let's get going here. So today is the 7th. No, the 8th. The 8th. Yeah, sorry. So more.
I can't read that.
Yeah. Some more integrating factors, or as someone else might call them, first order linear differential equations, right? Because we use integrating factors for first order linear differential equations. And just as a reminder, the format we must have, we absolutely must, wow, that's how you spell must? No, we must have the format y prime plus your function of either x or t, or whatever your other variable is, times y equal to some function of x. Or if it's in terms of t, y prime plus p of t times y equal to q of t. You have to be able to write it in that format exactly to be able to use the integrating factor. So here's an example that hopefully will turn out just fine. Yeah, I think that's right. I have to think, oh, wait, no. I'm almost making a dumb mistake. Okay, yeah, cool. I think I've got it right here. Let's see if we've got the following. Let me write it down here real quick. Yeah, I think that's going to work out. Okay, let's cross our fingers and hope it works. So let's say we've got the following. X times y prime plus 2y equals x times natural log of x. It's usually worth at least thinking about, could you separate it? I should say, right, we're solving this. Someone says we're solving a differential equation. It's usually worth thinking about, could you separate it? It doesn't look very likely here, right? If I isolate the y prime, it's going to be x natural log of x minus 2y all divided by x. And the x stuff minus the y stuff makes it really, really hard to separate those variables. So probably not. Let's move on. We are not written in the right format. We have an x times y prime. We need y prime isolated. So the first thing we should do is divide everything by x. So I'm going to get y prime plus 2 over x times y equal to the natural log of x. I strongly recommend writing the y part here separate from everything else. So it's your other function of x times y, just so it's easy to see what your p of x is. So here our p of x is positive 2 over x, and our q of x is natural log of x. So then we're going to find the integrating factor. Mu is equal to e to the integral of 2 over x dx. That's going to be e to the 2 times the natural log of x. For integrating factors, we definitely ignore the absolute value that would, that would normally appear there as integral of 1 over x. So for this integral up here, ignore everything. No plus c, no absolute value, just make it nice and pretty. You could leave it like this, but it's not in your best interest to do so. It is definitely in your best interest to simplify as much as possible. So we want to simplify this. Meaning we should rewrite it as e to the natural log of x squared, which is just x squared. Okay. I think it's worthwhile to show the steps. Your teacher might require you to show them. We can always jump to the end. So the steps are multiply everything by your integrating factor. So multiply the entire equation by the integrating factor x squared. So we're going to get x squared times y prime plus x squared times 2 over x times y equal to x squared times the natural log of x. I will point out, the steps I'm doing right now are steps that you might not have to do. I'll clue you in when you get to the place where you could have just jumped ahead to. So after we do that, we're going to simplify a little bit. I've got x squared times y prime plus x squared times 2 over x is just 2x times y equal to x squared times natural log of x. And the key thing to see here is that after you've multiplied the left-hand side by the integrating factor, the left-hand side is always just the derivative of a product. And it's easy to see what it is if you remember this little trick. Look for the thing that has the y prime and drop the prime. So instead of x squared times y prime, all of this here is x squared times y, the derivative of all of that. Product rule, derivative of x squared is 2x times y plus x squared times the derivative of y is y prime. Oh yeah, totally works. So here's what we've got now. By the way, I figured out what was going on with the camera last time. I know you don't care, but I care. I want you all to know I'm not crazy. I was projecting from the this thing here, not from the laptop to the screen. That's why I was having problems. Like, why am I doing this and it's not doing that? That's what was going on last class, among all the other problems I was having. So now we've got the x squared times y. The derivative of all that is equal to x squared natural log of x. So then we're going to say that x squared times y equals the antiderivative of x squared times natural log of x dx. And then not being finished, but writing it in the format that you're allowed to just jump to, we can say that in general, we're going to get y equal to 1 over x squared times the integral of x squared times natural log of x. And sometimes, depending on the professor, it's totally fine to jump straight from your integrating factor to this. So after we find mu of x equal to e to the integral of p of x, which in this case happened to be x squared, some people are cool with jumping to the solution, which is that y is equal to 1 over mu of x times the integral of mu of x times q of x, which in this case happens to be 1 over x squared times the integral of x squared times natural log of x. But we're not done, right? Just because you're allowed to say that's the answer, you still have to do the integral here. So, I know I've said this like every time, I'm going to say it again. We can't cancel anything here, right? Those x squareds definitely do not cancel. We have to integrate this. And let's say we have to use, I've got a mixture of things. So it's either going to be a u substitution or integration by parts. It's not integration, it's not u substitution. Right? There's no good choice for u here. But let u equal natural log of x, my derivative is 1 over x. I don't have a 1 over x dx. But let u equal x squared, my derivative is 2x. I don't have a 2x dx. So here it's definitely going to be integration by parts. So for the integral of x squared times the natural log of x, all right, this is the one I feel like always throws people off. What's my choice for u? Is it x squared or is it the natural log of x? It is the natural log of x. Because, well, there's two ways to remember it. You can either say, because we pick u based on the acronym late, and we definitely have a logarithm. But also, if you were to pick u equal to x squared, then your dv is going to be the natural log of x. And if your dv is the natural log of x, then your v has to be the antiderivative of the natural log of x, which, although not impossible to find, is not easy to find. It's x natural log of x minus. You have to use integration by parts to find it. That's not good. So instead, we're going to let u equal x squared. Except we're not going to do that because we just said we're going to let u equal what, everybody? Thank you so much. And our dv is going to be the rest. It's going to be x squared times dx. Our du, the derivative of the natural log of x, is 1 over x dx. Our v is the antiderivative of x squared, which is x cubed over 3. And then our integral ends up equaling u times v minus the integral of v times du. We always have to be careful here. You just want to simplify this before you integrate it. So I'm going to rewrite this as the natural log of x times x cubed over 3 minus, let's bring out the 1/3. X cubed divided by x is x squared. And then we integrate, we get the natural log of x times x cubed over 3 minus 1/3 times x cubed over 3. So then that's just what this is here. So our actual final solution here is that y is equal to 1 over x squared times natural log of x times x cubed over 3 minus 1/9 times x cubed plus c. We do need that plus c inside those parentheses, so it is getting multiplied by 1 over the integrating factor. Yeah.
The one thing I don't understand is how you got x squared y on the top.
Right here.
Yeah.
So from this previous step, we had that the derivative of x squared times y is equal to x squared times the natural log of x. And then what we did to both sides, we said, well, if the derivative of this equals that, then this stuff here has to be the antiderivative of that. Or you could say we anti-differentiated both sides. I feel like that's less technically accurate, but it's perfectly fine as far as getting there.
I get confused because, like, I got the x squared y prime plus 2yx. I don't know how that turns into the x.
Totally. So it's not turning into x squared y, it's turning into x squared y prime.
Yeah.
But so in fact, let's talk more about this. So that's kind of the whole deal with the integrating factor. Let's go. We're gonna go kind of broad here for a second. So you might not want to write this down because it's not particularly useful. So generally we have this deal here: y prime plus p of x times y equals q of x. And we're trying to figure out how to solve this. And so what we do is we multiply everything by mu of x, where mu of x is equal to e to the integral of p of x. Okay, stuff's gonna get a little heady here, but it's perfectly manageable. So let me ask everybody, what's the derivative of e to the x? Cool. Real quick, just so we can check everyone's understanding here. What's the derivative of e to the x squared? E to the x squared times, yeah, I heard just 2 for a second, 2x. Or in general, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's how I've said it forever and ever and ever. So we want to find mu prime here. Check it out. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, but the derivative of the integral of p of x should just be right. So, but wait a minute here. E to the integral of p of x is also just what we're calling mu of x. Right? That's literally right there, right there. So I want to point out that the derivative of mu of x is equal to mu of x times p of x. Ask questions if you have them. Okay, so now we're going to multiply the entire equation up here by mu of x. So I'm going to get mu of x times y prime plus mu of x times p of x times y equal to mu of x times q of x. Okay, I'm going to rewrite it just slightly. I'm going to have mu of x times y prime plus mu prime of x times y equal to mu of x times q of x. What did I do? I replaced the mu of x times p of x with mu prime of x because we literally showed that they're equal to each other, right? Mu prime is mu times p of x. Always, every time, whenever you do this process, it always works out this way. That's why it's so kind of neat. But now look at this. This is exactly a product rule here. So this is the step where we're going to do the thing we say like, oh yeah, I know that if I do mu times y prime and I do the product rule, it's mu prime times y plus mu times y prime. So what I'm doing here is I'm taking this thing that looks like the derivative of a product and saying, oh yeah, that's the derivative of a product. Still equal to the same thing on the right-hand side. And finally, if the derivative of this thing is equal to that thing, then the inside stuff, mu of x times y, has to equal the integral of mu of x times q of x. And then finally, solving for y, we get exactly what we usually get. That y equals 1 over mu of x times the integral of mu of x times q of x dx. That is why this process works every time, because of how we're finding what mu of x is, and the derivative of mu is exactly mu times p. So back to the problem that we were actually doing for just a second. What we're doing here is when we're multiplying everything by x squared, we're literally saying, oh yeah, if you actually take the derivative of this, if you take the derivative of x squared times y, it's going to be, well, product rule, 2x times y plus x squared times the derivative of y, which is exactly what I've got up there, just written in a different order because I wrote it in the wrong order. And it always happens. Now, probably most of your instructors, if they're having you do this, are not asking you to show all the work. They're probably perfectly fine with you saying, I found mu of x, it was x squared, and then jumping to that y is equal to 1 over mu times the integral of mu times q. But not everyone is. So you should definitely make sure you understand what your professor expects. Do they expect you to start with this and jump to the solution? Or do they expect you to show these intermediate steps where you multiply everything by the integrating factor, show that the left-hand side is the derivative of a product, and then anti-differentiate both sides? I know for sure Dedell, when he teaches this class, definitely expects people to show those steps. I don't know if that's true for Alvarado or for Goldsmith or for Lee. But you should find out, right? Because I can't imagine that you won't have a question like this on your next test. And so you definitely should know what the expectations are as far as how much work you need to show. Should we do another one? Yeah, let's do another one. But that means I have to make up another one. Which is always, I always feel like I come prepared to class, and then I'm like, oh, but I don't have the thing I actually want. Oh, maybe it's right here. Maybe it's hiding from me here. No. Fine, we'll do. Sure, we'll do that. So I'll give you guys a slightly easier one to work on. So let's try solving this. Solve y prime minus 4x equal to 4xy, James, come on. Equal to 6. Is that going to be terrible? Well, let's make it a 6x squared. Let's see how interesting that's going to be. So I want everybody to start off by finding the integrating factor. That dx is looking awfully in the wrong place there. Oh, it's probably going to be hard. The solving, finding mu is going to be easy. The solving this is going to be a little bit ugly. That's all right. Or maybe not. Let's see. Okay. What's my p of x? Thank you so much. It's easy to miss the negative, so be careful, right? The format is always y prime plus p of x times y equal to q of x. So if there's a minus sign there, that has to get incorporated into the p of x part. The y is always positive, it's never negative y. Okay, cool. So that's going to be e to the negative 4x squared over 2, which is negative 2x squared. Not thrilled about that, but it's fine. let's show the steps. Well, let's jump to the end and then we'll come back and show the steps. So the solution would be y equal to 1 over e to the negative 2x squared times the integral of e to the negative 2x squared times 6x squared. I knew I was making a mistake when I said that, but okay. Not a mistake, just making life harder for all of us. So one thing I would do here before I did anything else is I would actually not write this way. Why am I writing 1 over e to a negative power? Let's be a little bit, I don't know, let's write it more nicely and just write it as e to the positive 2x squared times the integral of e to the negative 2x squared times 6x squared dx. To solve this, we have to use integration by parts. Now, we are in a situation here where we could, I might have done something impossible here. Sometimes I might have made life really terrible here. I think this is impossible, which is okay. We still are doing the right process, right? We could be like, well, teacher, you gave us a stupid problem. There's the best we can do. And I think that is the best we can do because integrating e to the negative 2x squared is kind of impossible on its own. I'm pretty sure we cannot do anything more with this. Sometimes people write bad questions. Like me, sometimes. Yeah.
It was kind of from like my last question. So it'll always be like the IT, like right here's the e negative 2x squared times y.
Yeah. Yeah, exactly. So if you're trying to show like the intermediate steps here, and you multiply everything by your integrating factor, you're going to get your e to the negative 2x squared times y prime plus e to the negative 2x squared times negative 4x times y equal to e to the negative 2x squared times 6x squared. And the easy way to show this, and it's always true, it is always true that this part here is always just take this part here, your integrating factor times y prime, drop the prime for a second. So write it as e to the negative 2x squared times y, but then it's just the derivative of all of that. It's always true. It always works. It's never not going to work. You can check the math, right? If I do the product rule, it's the derivative of y times the other thing plus y times the derivative of the other thing. And the derivative of e to the stuff is e to the stuff times the derivative of that stuff. Totally works. But it totally works every time, so you don't need to check it every time because it's always going to work this way. It's always going to be just y times your integrating factor prime. Cool. Yeah. Okay. I feel like I should actually give you one that, man, the problem is it's hard to make those problems up, as you might have noticed, as I just did it poorly there. And I, of course, didn't come with any on hand. Did I not really? Nope, not there. Let me look at, oh, there we go. There's the hand I was looking for. Let's try this one. Yeah. I know we did that one before, but let's do this other one. Sure. So let's pick something a little bit easier. Sure. Let's say we have t to the 5th times y prime plus 3t to the 5th times y equal to t to the 6th. Someone is clearly just taking this problem and trying to make it a one step harder by throwing in an extra t to the 5th everywhere. We could certainly divide everything by t to the 5th as the first step. Is this separable? It might actually be separable. We'll talk about that in a second. If I divide everything by t to the 5th, we're going to get y prime plus 3y equal to t. I don't think it is separable, actually. Is it? I don't know. I really don't know. Like, I really don't know until I do this. So it is worth asking the question. Is this separable? If I isolate y prime, I get t minus 3y. I have dy dt equal to t minus 3y. And no, it's not. There's no good way to write this as a function of t times a function of y. It can't be done. Not separable. but it's good to think about whenever you're asked to solve a differential equation. Is it separable? Great. If it is, do it that way. If it's not, this is what you're stuck with. And if someone's asked you to solve something and it's not one of those two things, they shouldn't have asked you to solve it. All right, so, all right, everybody find the integrating factor. It shouldn't be too terrible. All right, should be getting e to the integral of 3 dt, which is just e to the 3t. Cool. Let's show the work, because it's good to show the work. All right, so multiply by that. So we're going to get e to the 3t times y prime plus e to the 3t times 3 times y equal to t times e to the 3t. And as is every time. Okay, everybody, you should take a second and try to rewrite the left-hand side as the derivative of something. You should figure out what goes in there, and then after that, whatever was in there without the prime should be equal to the integral of t e to the 3t. All right, you should be able to write this left-hand side as the derivative of the product, e to the 3t times y. And then integrating both sides, you just get e to the 3t times y equal to the integral of t e to the 3t. And solving for y, well, solving for y is going to be 1 over e to the 3t times the integral of t e to the 3t. As expected, right? This is definitely our 1 over the integrating factor times the integral of q times the integrating factor. Right, that's what we knew we were going to get from the get-go. But this is all the work we would have done to get there. So it sounds like some of the professors using I of t instead of mu of t. Totally fine. It's the same thing. People just like to use an I because the word integral starts with the letter I. They're the same thing. But now we have to finish it, right? We don't just get to stop there. We have to then be like, actually solve it. That's the problem with this. It's like once you get to here, then we actually have to do the integral. So the integral of t to the 3t. Okay, we've got a mixture. U substitution or integration by parts. It's always the question. IBP. If it was e to the 3t squared, here we could do it, right? If you had the integral of t times e to the 3t squared, then you could totally do a u sub because the derivative of 3t squared would be 6t. The problem was with the previous problem, I had an e to the t squared, and I didn't have just a t down below. So that's why it was problematic. All right, so let's see here. Oh, I could have fixed that one so easily in retrospect. Oh, well. Oh, well. So our u is going to be, is our u t or is our u e to the 3t? Definitely t, right? The u is the, I don't have a log, so the next thing I look for is the any power of my variable. Oh, t to the first counts as any power of my variable. So u is t, dv is the e to the 3t, dt, du is dt, v is e to the 3t divided by 3. And then we rewrite our y as 1 over e to the 3t times all of the integral. So it's going to be all of u times v minus the integral of v du. So e to the 3t over 3 dt. And then we should integrate this. So that's going to equal 1 over e to the 3t. I've got a t e to the 3t over 3. And when I integrate this, I'm just going to end up dividing by another 3. Right? The integral of e to the 3t is going to be e to the 3t divided by another 3. So I'm going to be getting minus e to the 3t over 9 plus c. And the plus c is in the brackets to get multiplied by the 1 over e to the 3t. You can leave it like this. I more am a fan of multiplying it out and writing it as y equal to t divided by 3 minus 1/9 plus c divided by e to the 3t. Perfectly acceptable to write it either way. Let's throw on an extra little thing here. So this is our general solution. Well, let's say we had an initial condition. Let's say we know that y at time 0 is equal to 17/9. Now find the particular solution. Particular. What? I feel like there should be, isn't there an R there? Particular, P-A-R? I mean, it doesn't matter. It's a math class, but yeah, that feels right, I think. I don't know. Not the best spelling. It's okay. So plug in t equals 0, y equals 17 over 9 to get that 17 over 9 equals 0 minus 1/9 plus c over e to the 0. So we get 17/9 plus 1/9 equals c. So we get c equal to 18 over 9, which is 2. So our particular solution is going to be y equal to t over 3 minus 1/9 plus 2 over e to the 3t. Cool. All right. Good stuff. Let's look at some direction fields. Go away. Say goodbye. Okay. Yeah, I don't even need that. Let's go ahead and let's look at this direction field here. Hopefully you can, well, you all will have to tell me how well you can see, how well can you see that? Kind of okay. Let's see if we zoom. Let's zoom in a bit. Yeah, that's way better. That cool. Closer. Yeah, okay, that's better. All right. So there's a direction field, which we have not been given the equation for. What we're going to talk about. So one thing we often like to talk about here is where is the equilibrium, or what is the equilibrium? Now I know, unfortunately, it's kind of hard for you to take notes on this because like you can't just copy down what I've got right here. So I apologize for that. If I do, I think we might do more of this on Friday, and I will make copies for everyone so you can all like have a copy to draw on, which would be great. But I was running short on time today, so I didn't do that. So I'll talk about this a little bit, but we won't do too many examples of this because I know it's not super nice and not be able to take notes. So when I'm looking for the equilibrium, I'm looking for where what is equal to what. I know that's not a great question. When you're looking for the equilibrium, you're looking for where things are not changing. If things aren't changing, that means the derivative is right. So we're looking for where dy dt or dy dx, depending on the variables, is equal to 0. In other words, you're looking for, oh, sorry, oh, my picture's in the way. That's terrible. Kind of. Okay. We're looking for where we have horizontal tangent lines or horizontal little slopey lines there. So we're looking for horizontal lines. So I can see one place where I have a bunch of horizontal lines. Right there. All those lines are horizontal. So I can see that, yeah, that definitely looks like an equilibrium where, I don't know if you guys can see the numbers there, but that is where y is equal to 3. So it certainly looks like y equals 3 is an equilibrium. And, interesting. I didn't think about that. That's totally right. Yeah. Here's a question that might not be super easy to answer, but if you think about it, but is it stable or unstable? I don't know if I have a good intuition as to what it is, but if we think about drawing a solution curve, so sometimes you're given these asked to draw a solution curve, meaning you're supposed to like start somewhere and then kind of follow the path. So if I start there, well, the arrows tell me go that way, but then the arrows kind of point a little bit more to the right, a little bit less up. It looks like, oh yeah, if I follow the arrows, it looks like I'm getting closer and closer to the equilibrium. So to me, that is saying it's a stable equilibrium. It's kind of neat. Yeah, I really want to say a lot more about this, but what else can I say here? What else can I say here? There was a thing I had in mind to say, and it's now escaping me kind of. So yeah, this is I thought this was gonna be I was like, oh yeah, I'm gonna put these out, it's gonna be great. It's like, but then I realized you don't have them to look at. So let's look at one more here and kind of talk about how we might identify a thing. Let's look at this one, sure. Okay. Actually, are there questions about what I've said about this, or does it seem clear why we're saying that is a equilibrium? Okay, let's look. And so I will point out this differential equation, just so you all know what it is. This differential equation is the differential equation dy dx equal to 3 minus x. So whatever value x I pick, the derivative is 3 minus that. So for example, when I feel like that, oh, it's 3 minus what, James? 3 minus y, which makes a lot more sense, right? If it was 3 minus x and I set it equal to 0, I wouldn't get y equal to 3, I would get x equal to 3, but we know that y equals 3 is the equilibrium. Or if I set y equal to 1, then dy dx is equal to 2. So all along the line where y is equal to 1, all these little direction arrows have a slope of 2. There's really not a reason I would draw them all again, except to have something to do. Or if y was equal to 0, dy dx would be equal to 3. So down here where y is equal to 0, all the slopes are 3. And the further down I go, the more positive the slope of my little direction lines are. On the other hand, if I go above y equal to 3, like if y is equal to 4, then my dy dx is going to be -1. And all those slopes there are -1. And the higher I go, the bigger the y value, the more negative the slope would be. Okay, let's look at one more. Yeah, let's look at one more. Let's look at this direction field here. And I think you can read it. Yeah, so I want you all to think about, try to identify on your own for a second, where might I have an equilibrium? I see one line of equilibrium for sure. Anyone want to venture a guess? You don't have to, but if someone wanted to be brave and raise their hand and guess what an equilibrium might be, yeah. It is -2. Specifically, it's what equal to negative. Yeah, definitely y equals -2. There's also another one, although it's a little harder to see. Not y equals 0, because y equals 0 would be this line here. X equals 0. X equals 0, all of my direction lines have a horizontal, have a 0 slope. So equilibrium are both y equals -2 and x equals 0, which is not surprising if you know that the differential equation was x times y plus 2. seems pretty reasonable that the equilibrium would be x equal to 0 because that makes it equal to 0 and y equal to -2. And again, you could try to draw some solution curves here, but it gets a little bit weird, right? So like if I try to draw a solution curve starting here, and again, my drawing skills might be called into question here, you're going to kind of go down this way, this way, this way. It looks like we're getting closer and closer to that. But then, right, if you were more up here, you might kind of do this and not quite get down to that equilibrium there, and instead end up coming back up this way. So this is not something, unfortunately, that we have. There's not a lot of ability for us to ask students to draw these because there aren't the resources for it. Right? No one's going to be like, draw a bunch of graphs for me. Someone's going to grade them. They're more going to be like, here are some graphs. Which differential equation do you think that might have come from? And so that's probably what we'll try to do next time, is I'll try to have like smaller graphs. I do have something that I think worthwhile. I mean, I think it's all worthwhile to some degree. Oh yeah, thank you, Jolene. Y equals -2, right on. The other thing I was going to show you though is that there's lots of places you can go to graph direction fields. I personally think the one I'm using is pretty good. And if it's not already posted in Canvas, I will be sure to post it in Canvas. So this is, yeah, I mean, if it's not already there, I'll post it. But for this one here, you can do kind of lots of neat stuff. The thing I think is kind of interesting here. So let's just make up, not that. Oh my God. Can I do the thing? Maybe. So you can make all sorts of direction fields. Like for example, d by dx equal to 3 minus y, which is the one we did before. But that doesn't look very good. I don't see my equilibrium line at all because I didn't change my field of view, right? So to make this nicer, we should go back and change the axes to be a little bit more spacious, like -5 to 5 and -5 to 5. There we go. There, now I can see there's my y equals 3 equilibrium. And what's also kind of cool about this is if you click on it, you can see the path of travel. So like if you want to, if someone gave you an initial condition of x equal to 0 and y equal to -2, you can click down there at 0, -2 and see that, okay, yeah, the line through that is still going to eventually tend towards the stable equilibrium. On the other hand, let's change the differential equation just a tiny bit. Let's make it 3 plus y. Looks pretty similar, but look at this now. If we plot a point like say -2 or 0, -2, we're getting pushed away from the equilibrium. That equilibrium definitely looks like it is stable or unstable. It looks definitely unstable, right? We're getting pushed away from it, and it is unstable. In fact, trying to connect all the dots here. Oh my gosh, why are you in the way? There you go. If we had a differential equation of 3 plus y, you could see that that's going to give you an unstable equilibrium. So our equilibrium is y equal to -3. That's right, it has to be. And then we know that's unstable in either one of two ways. You are either welcome to draw the phase plot. And I can graph 3 plus y, right? So if y is 0, I get 3. And if this is 0, I get -3. So there's my phase plot. It's very unexciting. But certainly, over to the left, my derivative is negative, so I'm decreasing. And to the right of my equilibrium, my derivative is positive, so I'm increasing. Or you could say g of y is equal to dy dx is equal to 3 plus y, and g prime of y is equal to 1. And then if you plug in your point, your equilibrium. It doesn't actually change anything. But since the derivative is positive, that means we have an unstable equilibrium. So no matter which way you want to say it, both of these things lead us to the conclusion that y equals -3 is unstable. So it's kind of nice to see the connection between the things we've been doing with the phase plot or with the other, I don't know what you call this actually, but the other way we test to see if it's stable, and the actual direction field, which is over there. I'm like, you already saw it. You know what it looked like. I don't need to show it to you again. Okay. I think I said enough things. I mean, I can always say more, but that's fine. So on Friday, I'll try to come with graphs for everybody to graph. Oh, Friday, we have class on Friday. Don't come on Friday. On Monday, I'll try to come with graphs for everybody. And maybe by then your teachers will start talking about have started talking about stuff beyond chapter 7. But yeah, we'll come prepared to do things. Have a lovely 3-day weekend. We'll see you all on Monday, not Friday.